Hi, my name is Joe Wang, and I'm a scientist at Amazon with the Alexa organization. And today I'd like to talk about our paper, an audio-based Weakword independent verification system. In this paper, we discuss the problem of Weakword verification. Weakword verification is the problem of determining whether a user intended to wake a voice-activated device. Generally, when discussing voice-activated devices, there are multiple steps here. First, the device is running a model locally, a Wakeword model, that attempts to detect when a user says the keyword. This happens if it detects what it believes is a keyword, it then will send the audio signal to an automatic speech recognition system. And the goal there is to convert that speech signal into a text transcript of what was said before it then moves downstream and is processed by other systems to try to act upon what the user requested, and whether that be playing music in this case, or if someone asks to change temperature. Our problem is Wakeword verification, and this happens after Wakeword detection, but before speech recognition. And the goal here is to determine whether the user actually said the Wakeword, and also whether they intended to say the Wakeword. Oftentimes, the Wakeword might not be said. It might be something that's confused the Wakeword detector, and that might have made a mistake, and we'd like to detect that. Or it could be that the user said the Wakeword, but they didn't intend to wake the device. It might have been in conversation. Another possibility is it could be something like media caused the device to wake up. And we'd like to, in these cases, detect these false wakes and stop the device from responding and avoid doing speech recognition and taking an action. So if this was someone talking about how convenient it is to use Alexa to play music, you don't want your device to start playing music. One of the big issues here is that the standard Wakeword verification problem is relatively straightforward. It's a binary classification problem, but this becomes much more complex when you have multiple different wake words. So as part of Amazon's voice interoperability initiative, one of the goals is to be able to interact with multiple different agents on the same device. And this can be many, many different wake words. So for example, we recently launched Samuel L. Jackson wake word. The thing here is it's difficult because to scale across all these different wake words would require building different models and also having data sets to train these models for all sorts of different wake words. And additionally, this would then require running all these models in parallel because we don't necessarily know what wake word was used to wake the device. So to that end, we propose the problem of wake word independent verification. In this problem, what we'd really like is for any utterance, such as hey, some arbitrary wake word, play music, we'd like to detect whether the user intended to wake the device or not. To do this, we sort of make an assumption that the audio around the wake word is independent of the wake word itself. So for example, we assume that if someone asked Alexa to play music, or Echo to play music, or Amazon to play music, that the commands around the wake word itself should be similar. The other assumption is that the audio surrounding the wake word is also informative of whether the user intended to wake the device. So for example, if I was talking about a device in conversation, and I could say something like, using Alexa is so convenient to play music, the speech around it, the audio around the word Alexa in that case, is actually informative. And from that, we could interpret that the user did not intend to wake the device. So based on these assumptions, we propose building a model that uses the audio around the wake word, but not the wake word itself. And by doing this, creates a model that works for any possible wake word. To that end, our system operates by first taking the audio around the wake word, a small amount of audio before the wake word and a small amount of audio after the wake word. In this case, it was a half second for each, and extracting features. In this case, we use standard 64-bin LFBE features. These features are then fed into a novel network. So we propose using a two-path CNN. One path handles only the pre-wake word features, and another path handles the post-wake word features. And these are completely independent convolutional layers, so they have different filters. These convolutional layers are merged once we've learned some embedding, and then they're fed to dense layers to try to make the final prediction of whether it was a user that was speaking and whether they actually intended to wake the device. One thing we also do is we build in an adversarial objective. And in this case, the adversarial prediction is what the actual wake word was. And the goal for this is to make sure that we're not overfitting on specific wake words, whether that be bits of the wake word that happen to fall into that half-second pre-wake word audio or post-wake word audio, and also to make sure that it's not certain combinations of speech that lead to a bias for one wake word. So for example, it might be with certain wake words, it naturally flows that you say one word and another, they become sort of combined. And we want to avoid overfitting on that, and then not generalizing well to new wake words. So to actually test this, we build a model using data from Alexa and Echo wake words. As a baseline to evaluate performance, we also build a sort of standard CNN that uses the full audio. And we actually train these on data for these new wake words. What we'll do is we'll evaluate it on two wake words, Amazon and computer. And we build these baseline models with essentially a similar architecture as a single path from our proposed architecture, except we use twice as many convolutional filters, so that the model complexity here is actually greater than the model complexity of our standard one, to make sure that this isn't just a case of our new architecture and new approach having more functional flexibility. And so these models actually have a significant advantage, because not only are they more complex, they're also trained on data specific to those wake words. And there are specific models trained for each wake word. So rather than building a model using essentially out-of-domain data for the Alexa and Echo wake words, these are trained on in-domain data. And what we do then is compare our out-of-domain trained wake word independent model to these baseline models that are trained on in-domain data. So to compare performance, we first look at the Amazon wake word. And we look at the performance on examples that were detected by a wake word detector. How well do we do in terms of our false accept rate and false reject rate? And what you can see is the wake word independent model, which is trained with no examples from the Amazon wake word. It's trained only on Alexa and Echo examples, does reasonably well. It falls between somewhere in the performance range of between 10,000 and 5,000 trained examples, baseline trained using that many examples. And so this is pretty good. One thing that's kind of interesting to note here is that we consider a false accept if the user intended to wake the device, but they didn't say the Amazon wake word. They might have mispronounced it. They might have said a different word, but weren't thinking or aren't familiar with the device yet, don't know actually what the wake word is. It could be someone visiting and thinks the wake word is something different. And that's something that our model is inherently not trained to detect. The wake word independent model actually is trained to accept any wake word. So to further drill into this sort of impact, we look at the performance only on examples that were classified as non-device directed and media. And these are examples that our wake word independent model should do better on, simply because they are not dependent on the wake word itself. We can see for these examples that our model actually, the performance of our model improves. And for a wide range of false reject rates, we actually have a lower false accept rate than a baseline model trained on 10,000 examples. And so this sort of confirms our intuition that this model is useful and actually useful in detecting false wakes, especially with respect to media and non-device directedness. We do the same evaluation using the computer wake word. And in this case, again, we see that the performance falls somewhere between a baseline model trained using 5,000 training examples or 10,000 training examples. Again, we compare to a model trained, we compare on a data set that removes these mispronunciations or other false wakes and only keeps media examples labeled as media or non-device directed examples. And again, we see our performance improves significantly on these examples. One thing to note, there is also a sort of sharp transition point in a lot of these curves. And these are often very difficult examples that have high noise, or they can be things such as examples where there is label error. These are all annotated by human annotators, and so there's inherently some label error in many of these examples. And that's just one of the reasons why we see some of this behavior where there's sort of a minimum or a maximum performance that you can get in terms of the false accept rate for a very low false reject rate. And then the other side of this is some of these examples that are very noisy are sort of hard to tell. It's sort of unclear what the label actually should be. And so that can sometimes also contribute to some of the error arising here. But the interesting thing that we do see is for both of these two wake words, for computer and Amazon, this single wake word independent model trained without any data is able to extract meaningful information and detect when a user woke the device without intending to. And so we believe this is actually a promising result and shows sort of a good future direction to go in order to build these systems that operate on a wide range of wake words and scale well to that. And that allow for this sort of voice interoperability where you can converse with multiple different agents without needing to have multiple different models running in parallel and fusing the decisions across them. So yeah, I think that's the main result. Thank you so much for listening, and hope I get a chance to chat with you during the conference. Thanks.